Okay. Yeah. All right. So yeah, this problem here, it's pretty simple. But the first part of it is we need to figure out the output power of our system, which is going to be the thing that does this. So do you remember how to calculate power?
Hold on. I think I have it written down. Weight. No, sorry. Yeah, weight divided by time.
No, not quite.
Or is that velocity times? I guess I have a bunch of different formulas written down. So, I have V times what looks like I.
So that's correct. That's at 1. That is electrical power, so that is voltage times current. So here, let's write these out. V times I equals P, which is the same as voltage times current. Why we use a I for current, the world may never know. Actually, the world does know. It's because we use C for charge. But there we go. That's one of them. So this is electrical. What is mechanical power's formula?
Is that weight divided by what looks like torque?
Not quite. So weight is a force right here. And power, so I'll write it out over here. It is, you're probably seeing work, which is what's making you think of that.
Yeah.
Yeah, it's a little confusing, but it's work divided by time, which equals force times distance divided by time, because work equals force times distance, okay?
Yeah, I remember now. I get the weight and
so that is work over time equals power. And that is mechanical. All right, so now that we know that, let's go ahead and fill out the easy part of this problem. The whole problem itself should be pretty easy, but let's do this part. So if I wanted to find out the mechanical output power that needs to do this thing up at the top, what would I do?
So you would go, so the work will also go force is that 140?
Yep.
And then times 5 feet.
Yep.
Divided by 5 seconds.
Yep. Second. And in this particular problem, these cancel out. So you end up with 140 foot-pounds, which is a unit of work per second. And we can convert that to something more useful later. We'll be converting it to a joule, which is the sort of standard unit for power. But this is what we need to know for the next part of this problem. I'll give you a sec to write those down. Let me know if you've got them written.
Done.
Okay. So now we've got these options for motors for this problem. And the question is, which motor should we use, basically? We know that our power requirement equals 140 foot-pounds per second. There we go. I misspoke earlier, but watt is the power unit. Joule is a little different, but basically, which of these motors here is what we want to know. And so what we got to do, there we go, is convert this to a unit that makes sense for these motors. So we're going to convert it to a watt. And to do that, I mean, you can use an online converter, which I would suggest doing if you've got weird units, which in this case we kind of do. However, I do want you to know what a watt and a joule and etc. is.
Like,
what now?
like the formula to turn it into that?
Kind of. We just need to know how we define a watt. What is a watt, basically? And so watt, and this gets a little confusing. There's a lot of capital W's. You know, we've got work, we've got weight, and we've got watt. They're all capital W's. This is why we use so many Greek figures in engineering, is because we have stuff like this where you have a bunch of letters that all mean the same thing. But basically, 1 watt is equal to 1 joule per second, which is, joule is a unit of work. And if you put it over time, it's basically how much work you're doing in an amount of time, which is power. So, and that equals 1 Newton meter per second, because 1 joule is the same as 1 Newton meter. And that is equal to 1 kilogram times meters squared over seconds cubed, which is a little complicated looking, but it's actually not that bad. And the reason why is basically what you're saying here is meters per second squared. That's an acceleration. And then kilograms is basically the mass, right? And if you do these two multiplied together, you get a force, right? And then if you multiply force times distance, which is in meters, then you get work, and then you put that over seconds. And so what you end up with basically is, come on, there we go, is meters per second, which is your acceleration, times your mass, which is your kilograms, times another distance, meters, and then times seconds down here, because you're putting it over time again for basically power, which is a little complicated. The more important one is that you know that the standard unit is watts for power, and that the standard unit for work is joules. Okay.
Okay.
And so what we're going to do is, because this is in foot pounds, we're just going to do foot pounds lbs per second to watts. We're just going to use an online calculator. You can do the equation out, but that is not necessarily super useful. And basically 1 foot-pound per second is equal to 1.36 watts. Okay. And I'm actually going to show you a thing that I prefer to do for conversions. And it's something that is a lot of times used in stoichiometry, which is part of chemistry. But I just like using it because it's good to visualize. And basically what it is you draw like this kind of thing. It's kind of like a weird, it's like a pound sign or a hashtag without the second line. But basically, you write 100 and whatever your units are. So these are foot pounds per second, right? And then you write your conversion, which is this guy, in the second column. And you always want the same units to be diagonal of each other, because you're going to cancel them that way. So you write 1 foot-pound per second down here, and you then above it write the same amount in watts, which we can see that from this it's 1.36 1.36 watts. And what that does is basically you're now multiplying everything on the top and dividing it by everything on the bottom, okay? And so you could do this with a bunch of things. It's useful for stoichiometry for balancing chemical equations, but I like to use it for just any conversions. So what you do is foot-pounds per second cancel out, and then you multiply these guys, you multiply the top together, and you end up with watts because that's the only unit left. And so what you get is 140 times 1.36 watts. Does that make sense? I don't know if I got that. Did you say?
Yes.
Okay, cool. And that is 190.4 watts. Okay. So now the question is, of our motors, and I'm actually gonna erase a little bit. Of our motors, what's the best option?
The mini sim.
So yeah, the mini sim is a good option. It's close to what we want here for our power requirement. However, and you'll see this a lot, usually we choose whatever motor is right above it. And the reason why is because, let's, for example, say we've got our robot climbing, right? I don't know, he's got a winch up here that's climbing.
Is it like a failsafe?
So let's say something bumps it or hits it, or maybe the bar is not super stable and so it just moves down a little bit. Anything like that will cause an impulse force, which will exert more power or more torque on the motor temporarily. And so it's usually good to choose something that's a little above your power requirement at its working conditions. These are the working conditions here, and these are its max conditions. The reason why is you don't want to operate it sort of at its peak all the time, right? You want to be operating it as efficiently as possible. Does that make sense?
Yeah.
Also, another reason is, you know how we looked at those, like the graphs that kind of looked like that generally?
Parabola.
Yeah. So one of the things about it is if your graph is like this and this is torque, right? And this is RPM. RPM goes down as torque gets larger, right? And so one of the other trade-offs is if you operate it lower, closer to this end of the scale, then your RPM is higher, right? So usually choosing a motor that's a little higher up is a good idea. So we know that 190.4 is our the power required. So we know that these bottom two won't work, right? We know that this one's close, but to be safe, we'll choose the one just a little better, right?
Right.
All right, so we're gonna choose the sim. And I think its information is on the next page as well. Do you have this written down?
Yes.
Cool. Alrighty. So we are choosing the sim motor. We're gonna operate it at 30 amps because that is its working amperage, which was shown here. And we're gonna use a 1:30 ratio transmission, okay? Does that make sense?
Yes.
Okay, so now what we need to know is how much torque are we putting on the motor itself? Okay.
Okay.
And so basically what we're gonna do is we just need to go backwards on that gear transmission. So what we're gonna do is, and I'm trying to find, is it in here? Yeah, it is. There we go. I want to make sure you can see it. We're going to be using these guys. So just our normal gear train stuff. And specifically, we're going to be using this, this one, which is torque in, torque out equals E. And similarly, it's basically this as well. But this is the important one because we need torque in, torque out. Okay. So what we're going to do. Oh, did it delete that one? Yeah, it totally did. There we go. So what we're going to do is we're going to say, there we go. We have an 140-pound robot. It needs to climb a certain amount and export or output 190.4 power. So now we're going to look at its performance map, and that's where we're going to go from. Okay, so this is basically the motor's performance map, which we talked about a little bit. We can find this on websites, etc., right? So we know that its power has to be above 190. So we can basically get rid of anything in the power column that is below 190, right? Because that won't work. And then we know from basically the problem telling us that we have to operate it at 30 amps or lower. So if we put it right here at basically as close to 30 as we can get, that's where we're going to be looking. And we can say over here that power is good. It is above 190, so we're solid that, and it's pretty well above 190, so we're feeling confident. And then what we're going to ask is how much torque can it output, okay? And we're going to do it in inch-pounds because that's what we were kind of closer to at the beginning. And to make it simple, we're going to just use what's on the table instead of doing linear interpolation. What linear interpolation is, it's basically saying we've got these two rows of columns, and we want to find a value that's in between them. So you see how it's like 37 here and it's 28 here? We would do linear interpolation if we wanted to find 30 amps. So we could do that if we want to be more accurate. I'm not going to make us do that right now, but we will use this 28.8 right here because it is still within our working conditions and it is on the table, which means the table tells us that our motor, our sim motor, will put out 4.3 inch-pounds of torque. So we know now 190.4 watt needed, 4.3 inch-pound of torque provided, okay? And if you look at the motor, you can also see that it at that torque output will be able to do this RPM over here. So 4248 RPM. Okay. Does that all make sense how we got all those?
Could you repeat the part for 190.4?
Yeah, so the 190.4 watts is what we got earlier for our power calculation. So when we did this slide here, we ended up with 140 foot-pounds per second, and then we converted that to watts, and the conversion basically spat out 190. So the 190 watts is our power requirement. Does that make sense? Cool.
Yes, it does.
All right, so now we know that we have 4.3 inch-pounds of torque provided, and that will go 4248 RPMs. We now know that information, and now we're going to apply that over here to see, there we go, to see how much torque it's going to output at the sort of working end. So come on, there we go. And I'm going to use this slide because that's where we're going basically with this. So if we have a 1 to 30 gear ratio, which means torque is increased by 30, then we have 4.3 inch-pounds, right? And we're going to multiply by that by 30 to get our new torque, okay? Our output torque. So it's basically, this is the gear ratio. This is just what that means in torque terms. And so we need to do this to find our output torque.
129.
Should
I figure out the answer for that?
Sure. You wanna...
Yeah, 129 inch-pounds.
Okay. And then we got one more thing to do, which is our RPM, our output RPM. So we are starting off with 4248 RPM, and then it's going to be divided by 30. So what is our new RPM?
$141.6.
Okay. Okie doke. There we go. So solid. So now what we basically need to do is figure out if we want to climb the fastest, right? Then how big, you know, how a winch sort of like winds around a drum? What diameter of drum do we need? Okay. To get the fastest climb. That's the question. So what we're gonna do, we now have these pieces of information. So I'm gonna write them off to the side so that we have this middle space. So we got 129 inch-pounds, and we have 141.6 RPM. And we will erase them in the middle. Okay, so the way we do this is basically we know we have a 140-pound robot, right?
Right.
So if we draw a free body diagram of this winch, or just a diagram, this would be a side view of the drum, right? So the winch would kind of like sprawl around it like that, and then the cable would go up that way, okay? What we want to find is the diameter or the radius here, okay? And then we will double that to get the diameter. So basically what this is saying is over here at this edge of the winch, there's a cable going up, right? And that cable needs to support 140 pounds for the robot, right?
Right.
And so basically what we're going to do is we need to figure out the torque around this winch so that the motor can still handle it, okay?
Okay.
So basically what we're doing here is just, you know how torque is force times distance?
Right.
So we've got a force here, and we're looking for a distance, and we have a torque that it needs to meet, right?
So would we divide by 90 degrees, or would we subtract 129 inch-pounds?
So so we're not doing anything with the 90 degrees because so torque is defined as force times, or perpendicular force times distance, right? And perpendicular means 90 degrees. degrees. So you got a distance, and then 90 degrees from that distance, you've got a force, right?
So it's already
What we've
in
got. Yeah, that's what we've got here. So what we're going to do is we're basically just going to set the two equal to each other, right? So we know that this torque here has to be the opposite of the torque created by the robot, right? Does that make sense?
Yes.
Yeah, so this is the motor torque, and this is the torque created by the weight. So what we're going to do is 140 pounds, which is our robot's weight, times r, which is the radius, equals 129 inch-pounds, okay? Does that make sense?
Yeah, I'm just copying.
All right, so then what is r is the question.
Just 1 second. So what we would do is when we divide 140 on both sides?
Yep. So basically we cancel that out and we do divided by 140 over here. And what that equals is, you got an answer?
1.09 approximately.
1.09, 129 divided by 140?
Sorry, I think I did that back. Yeah, sorry, I did that backwards. 0.92.
Yep. So 0.92 inches is our 0.92 inches is our radius. So if we just double it, that becomes our diameter. So we know that 1.84 inches equals diameter. Okay. There you go. So now we know quite a few things about our system. And that is, we know how big our drum is, how much torque it's outputting, and how fast it's going. The important part is how fast it's going, because we may want to know exactly how fast this thing's going to climb, which I don't know if they've got a slide for this one. I don't think they do, so I'm just going to do it. Oopsie doodle. So we're gonna erase some of this stuff. We'll erase that. We will erase this. Let me know. Do you have all this written down?
Yeah.
Okay. I'm gonna double check. We'll leave that, and we will leave some of that. Okay. So now what we need to do is basically convert angular velocity to linear velocity. Okay. And that's not a difficult thing to do. It's pretty simple. Basically, what we're going to do is this is still a thing. There we go. Got angular, which is equal to, or sorry, r equals v. There we go. This little guy here, that's an omega. He's angular velocity. It's just how we write it. And some things about angular velocity. Angular velocity is theta over time. So normal velocity is distance over time. Basically what that is just, it's how much of an angle you change, you know, how fast you change over an angle. So what we basically do is we just say that if omega equals theta over time and velocity equals distance over time, I'm not going to write all this out. basically velocity equals radius times theta over time, because what that is like if we have a circle and we say, here's the angle that's changed, here's theta, and here's r, the distance of this arc here, and that arc is s, s equals theta times radius, okay? So basically the distance traveled here is the velocity of the thing, and that's how we define it. So if we just put that over time, and we have angular, right? Or we have linear from angles. So, so this is the thing we're using here. And from that, we can basically say this here, theta over time, is the same thing as omega, which is angular velocity. So if we just rewrite this thing, we can just rewrite it as omega times r, right? And since we have our omega, which is this over here, we can plug it in and we can find out how fast it's going to climb. Does that make sense?
Yeah.
Okay. So what we're going to do is 141.6 RPM, because that was our new RPM after the gearing, times our radius, which is 0.92 inches. Okay? Make sense?
Oh, yeah. Sorry, I think my mic is cutting out.
Oops. There we go. So what is the answer to that one?
130.272.
Yep. And can you tell me what units that's in?
RPM inches, if that's a thing.
So RPM stands for rotations per minute.
Right. Wait, would it be rotations per inch?
Not quite. It would be inches per minute. Does that make sense?
Yeah.
Okay. So this is not a super useful number for us. I guess if we wanted it in minutes, that'd be fine. But I would say we should have it in seconds, since seconds is standard. So what we can do here is we can actually do 130 inches per minute. Same sort of thing. And we're actually going to write it like this, per minute. And we want to convert minutes to seconds. I know it's easy, but it's nice to know how this thing works. So you can say 1 minute equals 60 seconds. Minutes cancel out, seconds. So you just divide these. So that is 2.17 inches per second, okay? So if we have that and we know how far we want to climb, right? We can figure out how long it's going to take us to climb. Does that make sense?
Yeah.
Okay, so let me know if when you've got this written down.
I got it.
So now what we're going to do is we're just going to take this value that we have and find out how quickly we can climb, okay?
Okay.
Sure that it still fits within our parameters that we originally set. So we can erase everything except for that. Okay, so this one's pretty easy. It's basically just 2.17 inches per second equals velocity, right? Velocity equals distance over time, right?
Right.
And our distance here is 5 feet, okay? Because we're trying to climb 5 feet. So we'll have to convert this a little bit one more time, but not badly. And basically what we're going to say is 2.17 inches per second equals 5 feet over some time, right? And that time is what we want, okay?
Okay.
So time is in seconds here, but we need to convert one of these two to the other one. Just because it's easier, I'll say let's convert 5 feet to inches. So that's just 5 times 12, which is 60.
60.
So 60 over t inches. So what do we do here? What would give us time?
What do we go? 2.17 times t equals 60 inches.
Yep.
And then you would divide 2.17 on both sides.
Yep. So what would we end up with for t?
$27.65.
Yep, and that is in seconds. So we know it takes us approximately 30 seconds to climb this distance, right? Does that all make sense?
Right. Yeah.
So, all right. So the reason this is useful is so it says basically here, it'll take us 30 seconds to climb 5 feet, right? With an 140-pound robot using a sim motor at 30 amps. Does that make sense?
Yeah.
So those are FRC things. 140 pounds is like the same as an FRC robot. A sim motor is a FRC motor. The reason why is that this problem was set up for FRC, but it doesn't matter what it's set up for. It could be set up for FTC the same way. So we could instead say, I don't know, you've got a 30-pound robot. That's a hefty robot, but still. You got a 30-pound robot and you're using a Andy Mark Neverest, right? And instead of wanting to climb 5 feet, right, we might want to climb, I don't know, a foot, right? We could say we want to climb 1 foot instead of 5 feet. And you could give it a time constraint. You could say, I want to climb 5 feet in 5 seconds, you know, anything of that sort. And you could use this information to find out exactly what motor you should use and what size drum on your winch you should use, stuff like that. Or you could not give it a time constraint originally. You could do all the math and stuff and then find out how much time it takes. Maybe it takes 10 seconds. And if you find that time, then you can say, okay, at the end of the match, it will take us 10 seconds to climb, right? So we need a lot. What?
Why would it take 10 seconds? If you're dividing 5 feet by 5 to get 1 foot, then you would divide 30 seconds by 5, so it would be 6.
What I'm saying is we're not using a sim and it's not the same weight. This is a different problem, right?
Oh, okay.
Yeah, so this is a hypothetical. Basically, we'd be saying, let's say our robot's 30 pounds and we're using a different motor. This is FTC proportions. But say you do all the math here and eventually you find out that that would take 10 seconds to climb, right? Then you could say, we need to sort of section off 10 seconds at the end of the match for climbing. We need to be like hooked onto the bar with 10 seconds remaining if we want to climb, right? And so basically what you can do is section the game off for yourself in ways that ensure that you do certain things. Maybe you want to make sure you climb, but you don't know, like when you're driving, you don't know, oh, should I keep trying to put this thing in the slot, or should I go climb? Like, do I have enough time for both things? This gives you a solid yes or no. I do or do not have enough time, right? You could say it takes me 5 seconds to drive to the bar, and it takes me 10 seconds to climb. So if I have 15 seconds left, I need to drop what I'm doing and go climb, right? Does that make sense?
Yeah.
So you can do it for all sorts of things. This one was a climbing problem, but you can do it for anything. You could do it for my robotics class. We had a challenge where you sort of had to like lift these little fake pizza boxes and put them into slots. So you were like, it was a pizza delivery challenge, but you could calculate how long it takes you to place each pizza, right? You could say, this is how fast my arm moves, and this is how quickly I can place a pizza, right? And then you could calculate how many pizzas you could place in a given amount of time. So you could actually do this sort of thing for all sorts of things, anything, any sort of system that you're using, to find out how long it takes approximately. And so you could mathematically show in your notebook, our team believes, and here's the math behind it, that we could place 20 pizzas and then go climb, right? Or you could say, during autonomous, we will be able to do these things because, and you can show that you know that you'll be able to do those things. Does that make sense?
Yeah.
Yeah. So basically, this makes your engineering section of your notebook look fantastic, because what they see there is that you've put in the work to ensure that those things are going to happen, right? It also is great, just not notebook wise, because it makes your robot way more efficient. If you do this for each system, then you will get sort of the maximum performance out of your robot, right? If you choose your motors correctly, if you choose your gearing correctly, if you do the statics for the problem, you can basically build your robot for the game with math first, so that everything works well during the game. So it's kind of like, I don't know if you're familiar with, like, I mean, I assume you play video games. Yeah.
Yeah.
Do you know what min-maxing is?
Mid what?
Min-maxing.
No.
It's basically taking stats for like a character and making some of them really high and some of them really low. And yeah, exactly. And it's so that you get the best performance out of your character for the things you care about. So like, say you're playing like Skyrim and you want to be like a stealth guy, you want to sneak around, then you put all your points into sneaking and you put none into magic or something, you know?
Yeah.
It's the same sort of idea. You look at the game and you're like, I want to shoot all of these wiffle balls into the vortex. So let me do the math for that. I am going to make myself very good at that, and basically ensure that my robot can do that really well, and I can mathematically show that it's going to do it really well. So I know that it's going to do it really well, right? And maybe you don't do it for another portion of your robot that you don't care enough about, that sort of thing. But basically what you're doing is you're pulling as much performance out of your robot as possible, right? So if I don't see FTC teams do this a lot, but if people would actually do the math behind their robot, then their robot would work 10 times better, you know? So that's kind of the use for it. this particular thing, this power requirement thing, is super important. And I would suggest that you find problems similar and just practice them. It can be literally anything, as long as it's something that moves within a certain amount of time, right? That is all you need for this type of problem. You can look over this lecture to sort of help you through it and figure things out. General physics videos are great too, but if you did this for all the systems on your robot, you could pick the perfect motors for every task. You could gear them all properly. You could show the force and torque analysis on them, and you could basically time frame everything for your robot and make sure that it's really good. I did really want to, during this summer, get into projectile motion, because there's typically FTC likes to do shooting games. I don't think we're gonna have time for that. I might have like a little like one-off course during a Thursday meeting or something if people want to come to do projectile motion, and basically that just works in with all of this stuff to basically show you how to shoot things well. You know, it's basically trying to figure out how the thing is going to arc. So yeah, but does this stuff make sense?
Yep.
Cool. One thing to keep in mind, do you have all this written down?
Yep.
One thing to keep in mind with just this in general, if we look back at our graph here, is just to be operating on that left side of the curve. If you're looking at motors, and to do sort of the motor selection, you will have to look up the motor on its website and find out its stall torque and stuff. But basically, on this curve, you see efficiency up here. Basically the purple line, and then the green line. The green line is power, and the purple line is efficiency. Around 60% efficiency is where you want to be, which is right here. Can you see my cursor?
No.
Cannot see my cursor?
No.
What about now?
Yeah.
Okay. So right about here is where 60% efficiency is. You can see by, if you follow it over and look at the efficiency column, 60. That's kind of where you want to work. If you ever get to here on the green line at the very top of this parabola, you do not want to go past that. If you go past it and you start working on this side of the parabola, you're burning your motor. Okay? Horsepower, which is a type of power, it's just a unit of power. Basically, if your power peaks out, right, and you start operating it past its peak, then it's burning up the motor and you're destroying your motor. Does that make sense?
Yeah.
Yeah. So always work on the left side of the peak of the parabola. Okay. Ideally, work at 60%, because that's where you're going to get the highest torque and the highest RPM. Okay.
Okie dokie.
So this is the generals of that. I mainly wanted to go over that power, the power calculations. Something quick, and I think I went over this before, is just this slide here. It's basically how to select a motor and like what's the most important. Most important thing by far is your power requirement. That's how much power you need out of it. After that, you want to kind of like, if you have two motors and one motor's super big and heavy and one's super light, and they put out similar powers, you want to go with the light one, right? So weight of the motor and transmission. Physical size is just how it fits into your robot. Back drive is whether or not it unwinds whenever it's not being powered. And then the rest of them kind of go down from there. But just keep this slide in mind. The main two things you want to consider when choosing a motor is how much power it can output and how heavy is it. Okay. And I think that's generally it. I did actually want to show you this. I think Jude asked about this, and he's not here, but maybe he'll watch the class. When I was talking about types of anti-backdrive that aren't powered, one of them is a mechanical one-way clutch. And I just wanted to show you guys what that was. That's this guy right here. I'll make him real big so you can see it. Basically, it looks like a ball bearing with these little teeth in it. And the reason why is, and there are cool videos, like you can watch a video, just look up one-way clutch and watch a video of a thing that looks like this. Basically, when it rotates like counterclockwise in this picture, these little rollers don't do anything, right? They just sort of sit there and it rotates fine. If it rotates clockwise in this picture, that roller gets pushed up into this wedge and kind of gets squished in there and prevents it from rotating anymore. So basically what this does is it allows it to only rotate in one direction, okay? And you can buy these. They're not that expensive. You can buy them in all different sizes. So if you bought one for your FTC motor, you could just mount it into your robot if you want a motor to only spin in one direction. Does that make sense? You're muted.
Yeah.
Okay. I just wanted you to see it because it's a very simple way for like winches and stuff, make sure that they don't unwind. Because you can just buy it. They are like all over online. So I think that's what I'm going to go over today. We were going to go over efficiencies and how to basically make this table here, but because there are few people here, I don't think we're going to do that. Efficiency is basically just how much power you get in and how much power you get out. It's power out over power in. So if you wanted to, you could make this graph or this table and the graph from it as long as you had the free speed RPM, which is the green one down here, the stall torque, which is the green one up here, and then their currents. So that's basically it. The power column you get by multiplying the speed and the torque. The efficiency column you get by dividing basically the mechanical power by the electrical power, and that gives you efficiency. And the heat column doesn't really matter. I think I'm gonna say that's gonna be class for today. If you have any questions, I'll be here. We've got another hour, but yeah.
Okay, well, thank you for this. Thank you for teaching the class. It's been really fun and helpful.
Totally. I'm hoping that during the season, we'll be able to do maybe some challenges or something every once in a while. I guess I can ask you, do you think at Thursday night meetings, we're thinking about putting together like a form for teams to fill out? And basically what it's going to be is like, I would like to request this mentor for this Thursday night meeting or someday to come and review and help with stuff. So you could like reserve Kyler or me or Mr. Smith to come and review something. Does that make sense?
Yeah.
Do you think that would be a beneficial thing? Like, do you
Yeah,
think people would do it?
Yeah, I think it's a good idea.
Okay, cool. Well, we'll probably do that. Kyler and I will host some like fun random courses throughout the year, but we'll see. But thank you for attending. You've been easily my most attentive and present student, and I very much appreciate that. So thank you.
No problem.
All right, well,
Thank you again.
see ya.
Bye.